complex one or something.
Thank you to those that emailed me. Thank you very much. And if you haven't done so, please send a message from your preferred email address to this email address with your first and last name. Just mention that you're from Math 351, and it's completely optional, but I really enjoy reading about you. So just tell me about yourself, your hobbies, your interests, why you're taking this class, what you hope to gain, anything really. It doesn't matter. So I will use this information to add you to my mailing list, and I will use this as information as attendance, basically. Right? So I will know who came to this class at least once. Now it was already interesting that there are some people here that study physics, that like physics, and maybe the first thing I'd like to mention, maybe you would find it interesting, there are two books that I really like. Both books I just half or quarter digested, but one is used as an advanced introduction to mechanics at MIT. It's called an Introduction to Mechanics. You need to know calculus. You don't need to know analysis for that. And another book that recently came out. By the way, this book I have it hidden on my website, if you can find it. So the other book, that's when you become very familiar with the subject, you might want to pick up. So Spivak, he wrote 5 volumes on differential geometry. So that's one of the branches that analysis develops into. And there is a book, it's called Physics for Mathematicians. And you might like to see how some ideas, really actually more advanced ideas than what we're using here, but ideas from analysis are used to describe physics. Okay? You have it, guys? So, just to recap, so a very primitive notion of number existed by the time of the Pythagoreans and probably well before. And numbers arose partly because of the need to measure length. So you have a length of rope, you can just keep it straight, and this way you have a straight edge. And by pinning the rope in the ground, you can draw circles, right? So they had very primitive tools. Those are called straight edge and compass constructions. And using those tools, you can kind of even come up with your own arguments, right? What you could do is you can take a piece of rope, maybe this length, the length of my marker, and call it unity. That's your 1. Now, you can clearly produce many such pieces, attach them together, and you can create a number line, you can create the integers. So integers are in this way natural. And what you can do in addition to that is you can multiply numbers. And you can divide one number by the other completely geometrically, right? And that's because by straight edge and compass, I'm not going to go over it, it's actually not a hard construction, but you need 2 things. You need the ability to draw a perpendicular line through a point. So you have a line and you have a point not on the line, right? Here is a line, here is a point not on the line. Using straight edge and compass, you can draw a perpendicular line that goes through the point. Okay? And if you are able to do that, just take twice perpendicular and you can create parallel lines. Okay? So using straight edge and compass, you can create perpendicular and parallel lines. And using this idea, you can then see how multiplication would work. Right? This is just by similarity of triangles. So if you want to multiply the number b that you constructed by the number a, all you do is you put a unity somewhere, and you put the length b somewhere. Okay? And then you can draw a line from this point to the point where the unity ends. And then you can place over 1, you can place the number a by which you want to multiply. And then what you have is you see those two parallel lines. By drawing those parallel lines and seeing where they meet, you construct a times b. This is clear because, again, the triangles have the same angles, they are similar, so one is scaled by a, so every other side is scaled by a. And therefore you created the product a times b, right? By the same idea, you can also create, you can divide, right? You can just have a similar construction that will allow you to divide the number. And if you think about it, it's pretty impressive, pretty neat. Dividing in half is not as hard as dividing into 17 parts. But in theory, at least, they could create precise division into 17 parts. So that is what creates the rational number system, right? M divided by n, integer divided by another integer, in our modern way of speaking. That was understood. Now, there is a sense in which this number line system, basically just having rational numbers is inadequate, insufficient in describing your naive notions of space, right? So one problem is the problem of taking roots. So in physics, in many calculations, it's useful to know what is the root of a number. But roots of prime numbers, we showed it last class, root of 5, root of 2, root of 7, and actually you can generalize it to roots of many other numbers. They are not going to be feasible as a ratio of rational numbers. Okay? So if you want all of space to be measurable, all segment of space related to any other segment of space, commensurability, you need to extend the number system. Otherwise you have, at least naively, you have paradoxes, like the paradox of the brick, like the paradox of speed. Right? If you know measure theory, we're going to see some properties of the rational number line, and you will see that the rational number line looks deceptively similar to the real number line. But yet you can then have properties like the sum of lengths is equal to 0. So you have a length this big or infinitely big, but if you chop it up to small segments, you will see that they add up to nothing. Okay? So let's try to see how that problem, what that problem might look like. So let's say the square root of p prime cannot be expressed as m divided by n for any m, n that are integers. That's the fundamental problem that the Pythagoreans first noted. Okay, so what you can try doing is you can try seeing which numbers lie below the root. They are like the root of p but smaller. So let's say those would be r, rational numbers that are positive, such that if you square the number, you get something smaller than p. Okay, so the set A is just of positive numbers, rational numbers. You remember Q just stands for the rational numbers. So you have the sets A, and you have the set B, which would be all positive rationals that when you square give you a value bigger than P. Okay? So observe the following. If I take any R belonging to A, let's call it R sub A, and I take any R sub B belonging to B, then R sub A will be necessarily smaller than R sub B. Okay? In other words, A is bounded above. And similarly, B is bounded below. So in other words, if A represents your height, right? So your exact ideal height would have been root of P. Then in a way, if I draw A vertically, there is a fuzziness. There is no height. In other words, for any measurement that you pick in A, you will note, and I'm going to show that, you will note that there is going to be a bigger number R that you can pick in A. And that's how you can just notice it. So you can just take, that's a bit cheating. So here is the intuition of how this is constructed. So you have, let's say, root of P, and root of P is equal to root of P minus R plus R. Now here, of course, I'm using something that is not justified. There is no root P. I'm going to get rid of it in a moment. Right? I'm going to create an inequality. What this thing is, by multiplying by the conjugate, I get that the first number is P minus R squared divided by root P plus R and plus R. Now, again, it's not acceptable to have root P. I want to get rid of it. So notice that if I replace root P by P, I create a smaller number because I'm dividing by a larger denominator. So that's bigger than P minus R squared over P plus R plus R. And notice this is a positive number, right? R squared has the condition that it's smaller than P. So P minus R squared is positive. And therefore, we take R and we perturb it by a possibly small number. So that is small. That is bigger than R. Okay? In other words, you can see that in A, if you take any element in A, you can always pick a bigger element in A. And this, in fact, can be used to create a sequence that will approximate root of P. There are other sequences more efficient, but this can be used to approximate. Just pick any initial number, right? Let's say you want to take root of 5. Pick an initial guess. Pick, let's say, 2, right? 2 squared is 4. It's not quite root 5. Now, if you pick 2, upgrade it by this number, that's going to be your next approximation. With each step, your approximation is going to increase and get better and look more like root of 5. Okay? So this, of course, when you write an analysis book, you eliminate all reference to root of P. This is just showing you how you think, right? How you can get this approximation. root of p is not an entity that we justified, therefore, in terms of rigorous mathematics, it does not exist. So the notion that something is wrong with that something is wrong with Q is, it's kind of like this, so P would be here. It's as if the rational numbers have holes. And those holes, again, I'm going to show you later, we're going to show that those holes are going to be not perceptible. They're going to be so microscopic, so minute, less than anything, less than any measure of length. But yet, somehow, the rational numbers feel perforated. They feel ripped apart. So we need to do something about those holes. So we make the following definitions. So we will say that S is an ordered set if there is a relation call it this by this less than sign, with the following properties. So first is that if we have x and y are elements of S, then one of the following holds, and only one. So, of course, either you see that x is smaller than y, or x is equal to y, or y is smaller than x. So that's what it means to be an ordered set, that there is an order that you can impose on it. This can be a very abstract order. And the second property is that x, y, z belonging to S such that x is smaller than y and y smaller than z, that will imply, so that's a transitive property that implies that x is smaller than z. Okay? That's the abstract conditions that we require an ordered set to have. So another definition that we want to make is that if S is an ordered set, and we have a subset E, then if there exists, that by the way is written using this symbol, so that means there exists. Okay? If there exists beta belonging to S such that x is less than or equal to beta for every x belonging to E, we say E is bounded above. Okay, so again, very simple definition, right? If there is going to be a measurement bigger than every member of E, then E is bounded above. And now for a slightly new idea. So again, S ordered, and we have that E is in S, bounded above. So suppose there exists alpha, and alpha has to belong to S, such that the following conditions are true. Condition 1 is that alpha is an upper bound. Of E. Condition 2 if beta is smaller than alpha, then beta is not an upper bound of E. In that case, alpha is called least upper bound. We also write alpha equal to supremum of E. Similarly, we define the infinity. Is defined similarly. So let me give you examples, and as I'm giving you those examples, I will explain the intuition. So remember the set that we had before? So we had the set A of rational numbers such that, let's say, the number squared is less than 5. And we have the set B would be the rational numbers, the positive rational numbers, whose square is bigger than 5, right? We cannot get 5 exactly. So A is bounded above. What does it mean? A bounded above means that there is a number bigger than all the numbers in A. Give me one such number. 5, right? 5 is bigger than x, where x is an element of A. Okay? So there is a number bigger than any element in A. Okay? You might even say that every element in B is an upper bound of A. But in terms of Q, right, if we view A and B as subsets of Q, it's natural that Q is an ordered set, right? What's the order? You just compare sizes. Or you take one number minus the other, and if you get something that is bigger than 0, you say, well, I mean, I don't need to over-explain it. You know the Q more or less, you know which numbers are bigger than others. So if I look at A and B in Q, they are ordered sets. A is bounded above, but does A have least upper bound? So again, I will begin the answer and see if you can complete it. So again, the upper bounds of A are in B. Are in B. But if I take any element in B, but if, let's say, B is an element of B, there will be, what will there be? Smaller one, precisely. Okay? So you understand what the least upper bound means. It means that you look through all the upper bounds and you can descend through them and you will find the smallest upper bound. That's going to be your supremum. Okay? B, there will be B1 smaller than B, again, so B1 smaller than B such that B1 is in B, such that, oh, in other words, that's enough. So that implies that A does not have least upper bound. You can also say that B does not have greatest lower bound. And when I mention this, again, very important that you should keep in mind where? In Q. Right? If we take our ordered set to be Q, in that set there is no least upper bound for A and no greatest lower bound in B. Now again, those are confusing or technical terms. So let's try to ask a question. Oh, by the way, Sam, right? Yes?
So we're looking at this example. Could you relate A's and B's to your definitions with E and S? So in that definition, S is ordered, E is a subset of S. Where
yes,
is
so
A,
S
where
is Q. S in this case is the rational numbers, it's Q, right?
Okay.
A is E. Okay?
Okay.
Okay? Now let's actually, again, a lot of letters, let's try to ask a simple question. Okay? What do you mean? What's the difference between maximum and supremum? Right? Supremum, again, right? So imagine that I'm a set of points, right? So just shrink me to a line. And just imagine that every point on my body, again, linear, let's not move right or left, just move along the buttons, right? Those are points in my set. Okay, I'm A. So what is maximum? What would it mean that my set I contain a maximum? And what's the difference between supremum? Would anybody tell me? Yes, in the back, your name?
Bart.
Bart? Yes, Bart, please.
The maximum would be like the very top of your head.
Yes, the maximum is the very top of my head, provided
That it's part of you.
part of me, exactly, right? So maximum is the biggest element in my set, okay? What's the difference between supremum? Supremum is the biggest element. In other words, the supremum, the least upper bound, it's if you go any lower, you will contain points that are part of me, right? But it might not be part of me, right? So supremum is a maximum that might not be part of the set. I'll give more examples. You will see. You should just supremum is not very difficult concept. Yes, please.
So for set A,
Right.
why is it not the case that 5 is the least upper bound?
Well, again, where, right? So one thing to keep in mind, you always have to think what's your universe. So in this example, we only constructed rational numbers. I sometimes, of course, cheat, right? When I mention root of 5, I cheat. I don't have notion of that. But if I think strictly in terms of my universe, it only contains ratios of numbers, okay? In that universe, in the universe Q, Q is my ordered set. A is bounded above. You gave the example that 5 is an upper bound. In fact, every upper bound that you will find two possibilities, right? Clearly, because no number squared equals 5, no rational number squared equals 5, clearly I either am in A or I am in B. And if you just think about the order with the rational numbers, we just how multiplication works and whatnot, you will see that any element in B, 5 is in B. Any element in B is an upper bound for A. Okay? The picture that you can actually think of is here is A, and so this is A, and here is B. Okay? That's the picture. So either the number that I picked, I square it and I don't get root of 5, or I square it and I'm getting something bigger than root of 5. Okay? Now, B does not have a smallest element, which means that there is no there is no least upper bound for A. Okay? It would have been here, so to speak, but there's no such thing as here. There is a notion of a hole that feels that there is a hole, I think. But I cannot point to it. Okay? So, let's see.
Okay, so square root of 5 doesn't count as the least upper bound.
Well, that's what we are gonna get into, right? The square root of 5 is gonna be that least upper bound. We're gonna modify Q and force it to have least upper bound property. But we'll get to that. Okay? That's how we will understand what root of 5 is. So I mentioned this, but let me just, since it's in the notes, I'll just mention it again. If we have E part of S such that E bounded above, alpha equal to the supremum of E if exists. May or may not be part, or an element, I should say better, be an element of E. So let's consider simple examples, right? So let's suppose that, again, we take S to be equal to Q, and we'll take the set E to be equal to all ratios of 1 divided by n, where n is 1, 2, 3, onwards. Okay? So please tell me what is the supremum of the set E. If it exists, of course. Maybe it's vacuous. Is there a supremum for that set? So I have 1, then I have 1/2, then I have a third, a fourth, a fifth, right? What is the supremum of this set? Raise your hand. Yes, please? 1. The supremum of the set is 1, which belongs to E. Right? 1 is actually an element there, so that implies that supremum of E is the same as maximum E. Okay? And now let's calculate the infimum. So what's infimum? It's the same thing but going from the other direction, right? So where I'm standing, my infimum is somewhere on the floor. Okay? If I'm a set, I'm bounded above, bounded below. The floor is where I search for my infimum. It's everything. So what's the infimum of the set? Sorry, you probably already see it. What's the infimum of the set? And your name, please.
Frank.
Frank, please.
0.
Absolutely, it's 0. And is 0 a member of the set or not? Is 0 part of E or not?
No.
No. I don't see 0 ever, right? I only see 1/2, 1/3, 1/4, but I never see 0. So this is not part of E. In other words, I can say that E does not have a minimum. Make sense? So in other words, again, supremum, just a generalized maximum that may be part of the set or not. So it's a little bit more general than maximum. Infimum is the same thing, but for minimum. Okay? So now, another definition. So, ordered set S has the least upper bound property if any subset E of S that is bounded at that is non-empty and bounded above has a supremum. Okay. So let me ask you a few questions. So question 1. See if you understand this. Does Q have the least upper bound property? I will abbreviate it as least upper bound property. Okay? Does Q have the least upper bound property? So do you understand the question? What the question is saying, if I find a set that is bounded above, will it contain a supremum? Will it contain the least upper bound? That's an idea necessary for measuring, right? So if you want to say, well, how high am I? How tall am I? Sorry, right? Then the answer is supremum, right? If there is no supremum, then you cannot truly say how tall am I. So in Q, can you say how tall am I? I am being Arkady being the set A. It's a good hint. Remember the set A.
No.
No!
No.
You cannot say how tall am I. So, no. Again, recall the set A of all rational numbers, of all positive rational numbers whose square is less than 5. So A is bounded above in Q. But has no upper bound in Q. Okay, so when I mention no upper bound, you always have to reference your universe. In the universe of rational numbers, the only universe we know right now, we pretend to know for sure, in that universe, A has no least upper bound. And therefore, Q does not have the least upper bound property. I exhibited one set that is bounded above, but that set does not have a least upper bound. Okay? Again, the problem of measuring. Okay? Question 2. I want you to tell me. I want to see if you can guess what it might be. If I take the empty set as a subset of Q, what would you write for supremum of the empty set? And for infimum of the empty set. And of course, the answer could also be it doesn't exist if you prefer. Yes, Sam?
Yeah, I was going to say your definition says any set in any E in S that is non-empty. So it being non-empty is a requirement.
Very nice. So let's say that I'm going to take this requirement and I'm going to scratch it. Right? The requirement is not so important, right? So now I'm going to say this.
Yes.
Right? I just want to see your logic there, right? Well, that's very good. Yes, very, very observant. You're absolutely right. Now I'm scratching it. So what can you say about the supremum of the empty set? Yes?
Well, the supremum is defined as some element of the set it's in that's bigger than every element in the subset.
So in other words, if I take the empty set, an upper bound for it will be any element that is bigger than anything inside of the empty set.
But there's nothing inside of it.
Which means?
Which means it can't have a supremum or an infimum, right?
Well, you know, you are right in a way, right? So I would say it does not have a supremum in infimum, but not because of what you mentioned. Okay? So here's what happens. Here, how do you verify that something is an upper bound for a set? You take a number and you test it against anything in the set. Okay? If that number is bigger than anything in the set, then it's an upper bound. Okay? Now I take any rational number. Take 0, for example. I take 0. Is there anything that will challenge 0 from the empty set? right? In other words, I can come to this class. I actually thought no one will come today. I thought I glitched last time, I scared all of you, you transferred to another section. My time is done, I'm at the end of my rope. But nice you came, thank you, right? So, but if you did not come, can you imagine what I could have done here? I could have stood in the class and said, I am the strongest person in the room. I am the smartest person in the room, right? Because there is no one to challenge me. Okay? And my statement will be absolutely true, right? It would have boosted my confidence. Do you understand? So the empty set, is anything gonna challenge 0 from the empty set? No. What about -5? Anyone challenging -5 from the empty set? No. So what is the supremum, right? -5 is upper bound, like 0 was. What is the supremum?
Anything.
The supremum is the least upper bound, the least number that will challenge. So there are 2 answers that are correct.
There's nothing or anything.
So what's the answer? What's the answer?
Nothing.
Is there a least upper bound? Wonderful, thank you so much, right? It's not a number, so yes minus infinity, but it's also not the least upper bound, it's not a number in our context, right? But it's easy to just have abuse of notation and say that if minus infinity, if we just include this and consider it a number, that you can then force it to be a least upper bound, okay? So the answer is, you might say I, supremum of the empty set does not exist. That's fine based on our definitions, does not exist, let's say, in Q. In Q, right? Because I can say that the empty set is smaller than, let's say, smaller than 0. And you know I'm abusing notation. What I mean by that is anything in the empty set is not going to challenge 0. Anything in the empty set is not going to challenge -1. Nothing will challenge the empty set. Yes? Nothing will challenge the empty set. So therefore, that's one way to say that, but you might as well just say that the supremum of the empty set is equal to minus infinity. That's a nice way to just say that you can go anywhere down. Now, what about the infimum? Can anybody tell me what happens to the infimum? What about infimum of the empty set? What is that?
It would make sense that it would be infinity based on that, but
Right. How do you think? Here's how you think mathematically, right? The statement is true unless there is something to challenge it to make it false. Okay? If nothing challenges to make it false, it's true. So empty set. Is there, so you take, let's say, the number 10. Is anything in the empty set bigger than, smaller than 10? Right? No. That means nothing is smaller than 10, so 10 is a lower bound. Right? So you can go up like this, right? So that would be plus infinity. And again, you're just as well justified to say it doesn't exist because there is no greatest lower bound, right? You can go up and up and up, and all of those are lower bounds for the empty set. Okay, that's one reason you don't like the empty set. You might say non-empty, although that's just a hassle you don't have to bother with. Okay, so the non-empty part makes this weird situation. You would expect supremum to be bigger than infimum, correct? You would expect the bigger thing, you would expect my lower height to be smaller than my upper height. Yes.
Just curious,
Yes.
does this have any application anywhere? Like if an is
With the empty set, you see, you make a statement. You want to make a general statement, and the empty set might, technically speaking, make the create cases, right? Create pathological cases. So that's all. You have to deal with the empty set just as you have to deal with subsets. In a way, just so that we don't have a nuisance for it, we can define the supremum to be minus infinity. We will do that because when we deal with real numbers, you will always want to say supremum and infimum, and you don't want to consider the case where the set is empty. You want a general statement. So it's not particularly important. At least, no, I cannot think of anything off the top of my head that it's important. Okay, just logic. It's like you can say Newton's law is true, right? That the body will continue moving in its state of perpetual linear motion if no force acts on it, right? But that's the type of thing, right? But you always have forces acting on the body, even if you take Newtonian mechanics to be true. Okay? So here is a theorem. So suppose S is ordered set with upper bound property. Okay? What does this property mean? Take any set bounded above, there will be a least upper bound. Then the following is true. Then S has the greatest lower bound property. What is the greatest lower bound property? Would anybody tell me? I didn't define it, but I'm sure you understand what it is. What's the greatest lower bound property? So you have this pen. Is it bounded below if you consider it on a line? Yes, right here is the lower bound. Okay. Now, what's the greatest lower bound? I just push my arm up until I so to speak touch the pen. Okay. So we have a set that has if we have a set that has the greatest, that has the least upper bound property, it has the property that if you take a set B that is bounded below, it will have a greatest lower bound. Okay? In other words, sets that have lower bounds have infimums. If they have supremums, they have infimums. Yes.
But didn't we define one where it wasn't true? We looked at that
yes,
one.
Well, the point is if you have it. Right?
Yeah, but
Q does not have it. Q does not have the least upper bound property. Okay?
Okay.
We saw that Q doesn't, right? We saw the set, all the irrationals whose square is less than 5. They are bounded above, but there is no supremum. So it does not have least upper bound property. Okay? It will not have the greatest lower bound property as well. Those things, they come together. The point of this theorem is that those things always come together. If you have the supremum property, the supremum always exists. That's basically, if you want to make it very short, just say least upper bound property, supremum always exists. Greatest lower bound property, infimum always exists. But you understand what it means always to exist. Supremum always exists means bounded above, least upper bound. Infimum bounded below, greatest lower bound.
So let's look at 1 over n again.
Yes.
1 over n is an ordered set, right?
1 over n is an ordered set, yes.
Where n goes from 1 to.
So you want to take it as your s, 1 over n or as your s.
Yeah.
Yes. Good.
We have a lower upper bound.
Well,
We have that 1.
no.
Right?
Well, so 1 again. If you want to measure s, right? S is is it's bounded above in itself by 1, but it's not bounded below in itself.
Exactly. So
So it's fine. But does the set have the least upper bound property? That's a good question. Did anybody understand what was just asked? Right. So you have the set. Just erase everything in the universe. You have 1, 1/2, 1/3, 1/4. That's your set S, right? It's ordered. I can compare sizes in that set. Does this set have the least upper bound property? Does the set have the least upper bound property?
one is greater than every other element in the set.
Yes, but again, you are looking at only S. The property is a little bit different. What is the property? Take S, take any subset of S that is bounded above. Does it have a supremum? Okay? S is bounded above by itself, it has a supremum. So, good question. So, let's sidetrack question. So, we take S to be the set 1 over n, where n is a natural number. Okay? Does S have least upper bound properties? And does it have the greatest lower bound property? Let's see if we can answer that. So here's how you begin, right? You have to say, well, that E, a subset of S, be bounded above. Okay? Do we contain Supremum?
Wait, is it that you said if any subset of S has a supremum, right?
Or any bounded subset, right? So if you take a non-bounded subset, then it doesn't have to have supremum. But if I take a bounded subset, bounded above, it has to have a supremum. That's the least upper bound property. Okay? We're not going to do it we're not going to do it formally, actually, right? Because this subset is a subset of R. If you understand R, you can actually argue it pretty well. But intuitively, let's just answer it intuitively. Will it have a supremum?
Let's define E, for example, to be not starting from 1, but from 2, going to n.
Well, it doesn't matter where it starts, right? The question is, I found the E and I found it's bounded above. Okay? What do I do? Bounded above. What's the biggest upper bound you can have? In this case, you have a biggest upper bound. If it's bounded above, what's the biggest one? 1. So I say 1. Is it my least upper bound or not? You see, I jump in discrete steps. 1. Is it also the least upper bound? If not, I go to 1/2. If not, I go lower and lower and lower. Okay? I cannot go forever, otherwise I erase the entire set. Agree? So at some moment it has to stop, and that has to be my upper bound. In fact, it will be a maximum.
Okay.
Right?
Yeah, so it does.
Right. So bound above. So E has, or supremum E exists. Supremum of E exists and equals to max E. Again, I'm not being very thorough, right? But if you know that this is a subset of real numbers, if you know it's closed, many ways you can just argue it if you know something about the real numbers, and probably you can argue it even without. But it exists, so that means that it means S has the least upper bound property. Make sense? Okay. Q doesn't, but S does. Does it have the greatest lower bound property? Well, if you prove this theorem, obviously. But think about it. Greatest bound property also, greatest lower bound property also exists. So, in Supremum, if E is bounded, if let's take another set, so let's not confuse with this E. If V is a subset of S bounded below, infimum of V will also be minimum of V. Intuitively, what you do is it's bounded below. Okay, bounded below means that there's a number of the form, let's say maybe 1/1,000,000. Right? There's some number that is bound below. So what you do is you start going up, right? Going up, and eventually you're in the set.
And it has to have a minimum because it's a subset, and so it has to have a defined number of elements.
Well, in a way it's discrete. So if it's bounded below, the only thing that can bind it below is 1/n, right? So there is going to be some number, let's say 1/100. Right? So I only have 100 steps to go up until I find its minimum. Right? 1/100, it's a lower bound. Now 1/99, is it a lower bound or not? If not, I move up. Right? So if not, then I already found it. Right? If it's still a lower bound, everything is still above it. So I move up. There is just no room for this space V to reside.
But S is an infinitely large set, right?
Yes, it's infinitely large, correct.
And can go as high as you want. So if V is a subset of S, V can also be infinitely large and can go as high as you want.
V, if it's bounded below, it cannot be infinitely large. Right? If it's bounded, you see, in this universe, if it's bounded above, it can be infinitely large, but if bounded below, it has to be finite. And if it's finite, you can find the minimum.
So we have to first define that it's bounded below or above before we can.
Yes, that's what the property is. The property is if something is bounded below, then the something has a floor. If it's bounded above, it has a minimal ceiling, right? You can kind of press the ceiling until you touch the top. That will be the supreme. Make sense?
Yes.
Our class is over at what time?
6:50.
6:50. All right. So let's try see if we can prove this theorem. Proof. So I'll first make a drawing for the proof. So you understand what we have? We have a subset S, whatever that means. It's some abstract set, and it's ordered and it has the least upper bound property. Okay? And I want to show it has the greatest lower bound property. Okay? So what I do is let V be bounded below. Below. Always in S. I will stop writing it, it's annoying, but always in S. Bounded below, so I can kind of draw a schematic of B, so this is B. I don't know, maybe it goes on up forever, but there is a bound, it's bounded below. So I'm going to define the set of all its lower bounds. So I'm going to say this is L, and let L be the set of lower bounds. So L is the set of all, it's the set of all little l's belonging to S such that L is less than or equal to B for any B belonging to capital B. Make sense? So L is the set of all lower bounds. Then L is not empty. That's by hypothesis. B is bounded below, so there's going to be at least one number that is smaller than anything that B has. L is not empty. And another thing that you can observe, every element in B is an upper bound for L. You agree? Just like in the picture, anything, any element in B is going to be bigger than all the elements in L because they are the lower bounds. Okay? Now, the picture suggests where should we search for the greatest lower bound? In terms of L, what should they take? What should they do with L to find the greatest lower bound? Take the supremum, right? It will actually be the maximum, you're right, but supremum. So this thing looks like supremum L. Let's put a question. Okay? So let alpha equal to supremum of L. So then the following is true. So then if I pick any number bigger than A, then if beta is bigger than alpha, beta is not an element of L. Because alpha is the supremum. Go anywhere up, and you cannot find elements in L higher than the supremum, correct? So there exists a B belonging to B such that B is less than beta. And what we have shown is that no beta bigger than alpha is a lower bound. No beta bigger than alpha is a lower bound. Now, on the other hand, we want to also mention that notice that alpha is a lower bound. If not, there will be, again, there will exist maybe B1 belonging to B, such that B1 is less than alpha, right? But that would imply, but then B1 is an upper bound of L, which would imply that supremum of L will be less than or equal to B1, which is less than alpha. Okay? So that does not work. You see? I mean, you can draw the picture, so the picture is already suggesting what you should do, but formally speaking, you see why this is now approved that the least upper bound property guarantees the greatest lower bound property. Make sense? Everything understood? Just don't get lost in the details. Draw this picture, try to prove it on your own, right? Just think about this picture, you see what happens, right? So this is, nothing bigger can be a lower bound, like in the picture, right? And this has to be a lower bound itself, so that makes it the greatest lower bound. That's it. So I think no time for anything else, right? Have a good one.